Welcome friends. We are dealing with experiments related to operational amplifiers and we are discussing the experiment on operational amplifier applications. Today we will be dealing with the differentiator circuit. The differentiating circuit produces an output voltage which is proportional to the rate of change of the input. You can see the figure for differentiator circuit. You can see a capacitor is connected to the inverting terminal, that is pin number 2, and to the resistor, and input is connected to inverting terminal through this resistor and capacitor. Non-inverting terminal, that is pin number 3, is connected to ground directly, and in feedback between pin number 2 and pin number 6 a resistance, that is we call it as a feedback resistance, is connected. Plus VCC at pin 7 minus VEE at pin 4 are connected to bias the operational amplifier. Considering the DC voltage applied, although it is not, but say when you apply a DC voltage here, the C1 acts as an open circuit, and as we know the non-inverting terminal is connected to 3, the voltage at inverting terminal is also same as that of non-inverting terminal, that is potential at this point is also 0. Now there is no signal at all at pin number 3 and pin number 2 is connected to pin number 6 through resistor RF. Now this circuit we call as voltage follower, but as there is no signal at all, the output will be grounded until the input is connected. While considering the AC input, for positive going voltage, that is the positive half cycle of the voltage, current flows in this direction. I'll call it as I1, flows through resistor R1 and it reaches C1. And as we know, I1 value is much higher than the input bias current of the op amp. So effectively all the current, that is all of the I1 flows through R1, C1 and it goes towards RF and reaches the output terminal. As previously discussed, the left side of RF is connected to pin 2 where the RF is connected to pin number 2 where the potential is 0 because of non-inverting terminal is grounded. So concept of virtual ground comes here, and the circuit acts as an inverting amplifier, and V0 can be written as the current times resistance with a negative sign as it is an inverting amplifier. Now let us consider the case of triangular waveform as shown here. When positive going, it has a rate of change, it can be identified very easily as a small change in voltage with a small change in time, del V by del T. Now assume that the capacitor voltage is 0. Capacitor voltage is 0 when the input is 0, and also assume that resistor R1 has no effect on capacitor charging current. Okay, we are considering R1 as an ideal resistance. Now when the input increases from 0 to Vp, in this waveform I am showing you, when it increases from 0 to Vp, then capacitor charges to Vp. So the capacitor voltage changes by del V times. So earlier it was 0, now it is Vp. So that change of voltage stored on capacitor, I will note it as del V. Okay, and time to change the voltage over capacitor is nothing but small change in time, that is del T. During this time say the capacitor charging current is constant as the input voltage of change remains constant. It is a linear waveform, so change is constant. So with this constant charging current, I can write C1 as current times the small change in time divided by small change in voltage, or you can write I1 as C1 small change in voltage to the small change in time. Therefore, I can write V0 as minus of, I am substituting I1 in this equation, minus of C1 small change in voltage to the current multiplied by the resistance RF. So this the V0 can be written as minus C1 RF, the change in voltage to the change in current. I'll call it as equation 1, and this shows that the output voltage is directly proportional to the rate of change of the input, or you can say the output is the derivative of the input. You can note here the differentiator output of this circuit is inverted, that is the output voltage is positive DC level when the input is negative going, and the negative voltage level when the input is positive going. The one more significance of resistance R1 is it is included here to prevent the circuit from the high frequency oscillations. Now we will conduct this experiment. We connect the circuit diagram on the breadboard. We will apply some input, and the input waveform will be of triangular wave, and we will check whether it gives me a square wave or not. So this is the signal generator used to apply the input, to apply the positive and negative VCC to the op-amp dual power supply, and a DSO or a CRO can be used to view the outputs. Now on the breadboard we have connected the differentiator circuit. You can see a resistor is connected. From other end of the resistor a capacitor is connected to the pin number 2. At the start of this resistor, input is connected from the signal generator. One more resistance, that is a feedback resistance, is connected between pin number 2 to pin number 6. At pin number 7 is connected to plus VCC, pin number 4 is connected to minus VEE, pin number 3 is grounded. From DSO we have taken 2 wires. This is connected to the input, and the other channel wire is connected to the pin number 6, that is output. So on the DSO screen we will be checking both the waveforms, that is input and output, at the same time. Let me turn on. I will turn on the signal generator, the dual power supply, and the DSO. You can see the frequency I have chosen nearly 300 Hz, and the voltage is around 3 volt, 3.08 volt peak to peak. So this circuit is operating, and you can see the output on the screen of DSO. So for an input of triangular wave, the square wave output can be observed on the screen. Hence, we conclude that the op-amp can be used as a differentiator circuit. Thank you.